We're in Rosen, Discrete Mathematics and its Applications, section 9.3 on representing relations. Here we talk about the directed graph or digraph method for representing a relation. So a digraph is a set of vertices and a set of ordered pairs, or which would be called edges or arcs. The vertices correspond to the elements in the set on which the relation is defined, and the edges correspond to the ordered pairs in the relation. And when we have an edge, it's going from a vertex, which is called the initial vertex, to a vertex B called the terminal vertex. And anytime you have an edge starting and ending at the same vertex, it's called a loop. So here we have some ordered pairs. You can suppose that they might represent a relation on the set containing A, B, C, and D. And I would need to draw a vertex for every one of these. And then an arrow for the edge that represents each ordered pair. So I'll go ahead and put the image up. So here's my vertices A, B, C, and D. And you can see that we have an edge going from A to B to correspond with the first ordered pair listed. Notice that B has a loop, and that goes with the ordered pair BB. Notice that there is no edge B to A because BA is not in my relation, but DB and BD are both in on the digraph because BD and DB are in the relation. So there'll be the same number of edges as there are ordered pairs in the relation. Let's look at it the other way. We've got a directed graph that represents a relation on a set. Here the set is the set containing 1, 2, and 3. What are the ordered pairs? I see that 2, 1 is an ordered pair, but not 1, 2, because there's no return arrow. On the other hand, both 1, 4 and 4, 1 will be in the relation. 1, 1 is not in the relation because there's no loop, but 2, 2 is in the relation. And here's the solution. There'll be, again, the same number of ordered pairs as there are edges in the digraph. All right, so we can also use the digraph to detect the properties of relations on a set. Remember the 4 properties: reflexivity, transitivity, symmetry, and antisymmetry. And how do we find them? Well, we'll just look at the digraph and we'll check. If you have reflexive relation, you must have a loop at all vertices. To have a symmetric relation, if xy is an edge, then yx must also be an edge. In other words, xy is in the relation, then yx must be in the relation. Antisymmetry, that if xy is an edge where they're not equal, then yx cannot be in the relation. Transitivity, if xy is in the relation and yz is in the relation, then xz must be exhibited in the digraph. So we'll step through several examples. This first one, is it reflexive? Well, no, because I don't have a loop at every vertex. Is it symmetric? Yes, it is trivially because there's no edge from one vertex to another, so we satisfy the condition vacuously. Similarly, it is also antisymmetric Since there is no edge going between any two non-equal vertices, then we satisfy the hypothesis in the definition of antisymmetric. And then finally, the same will be true for transitivity. We satisfy, the hypothesis is always false, so it is trivially transitive. Okay, how about this graph? Clearly there's not loops at every vertex, so it's not reflexive. Is it symmetric? Well, these two arrows suggest the possibility of symmetry, but we have this arrow by itself between A and B and not returning, so it is not symmetric. Also, because we do have arrows going back and forth between B and D, it is not antisymmetric. Is it transitive? Well, if it were transitive, I have AB and BD. I would expect an arrow A to D if it was transitive. It's not there, so we say it is not transitive. All right, next example. Clearly no loops at every vertex, so it's not reflexive. It's not symmetric because I have arrows going from C to B and not returning. And then it is antisymmetric because every time I have an arrow going between vertices, there's not a return arrow. Is it transitive? I have AC and CB, and AB is in the relation, so it does appear to be transitive, and it is. All right. Last example. Is it reflexive? Again, no, not loops at every vertex. Is it symmetric? No, I don't have return arrows. Is it antisymmetric? Yes, because I don't have return arrows, it's antisymmetric. And is it transitive? It turns out, yes, it is transitive trivially. We never satisfy the hypothesis for the transitivity definition, so it's true vacuously. I never have two arrows where you have the tail of one arrow touching the head of the other, thus forcing us to look for the shortcut arrow. That is some examples of using digraphs to look at properties on